Topic is vector quantization using self-organizing map. This is a very important, this is based on a very important property of the self-organizing map, and that's about the approximation that it makes from a continuous space to the discrete output space. Okay. So, making use of that property, what is known as a vector quantization, that can be carried out. So, we will be talking mostly about that in this lecture, but before that I would like to clear some of the doubts which might have cropped into the students' mind in the last class. That is about the way the topological ordering is taking place. I think you need to get a feel of how the topological ordering actually happens. So, we will try to clarify the issue today. Now, as we were taking the kind of example in the last class, that let us say that we have got an input which is consisting of just two elements. So, it is a two element vector, let us say x1 and x2, these are the elements of the input, and supposing in the output we have got a lattice of neurons. Okay. So, let us say that these are the output neurons organized in some lattice, let us say two dimensional lattice. We can have one dimensional lattice also, and let us say that here we have got the two inputs x1 and x2. So, what happens is that this x1 and x2 will be connected to all these neurons at the output, right. So, x1 and x2 will be connected to all this. So, with each of these output neurons there will be a two element vector wj. Okay. So, a two element wj vector will be associated where j is equal to 0, 1 up to L, where there are L number of neurons in this output layer, correct. So, we have got two element input, that is the x vector is two element, and wj vectors individually are all two elements. So, let us try to visualize this picture. So, we will be having the input variables, the input vectors should be picked up from a two dimensional space, and let us say that we pick up the x1 and x2 from a space which is defined as follows. Say we take x1 lying within 0 and 1, and we take x2 lying within 0 and 1. So, we actually create a space like this. Let us say that this is our point of origin, that is 0 0, and in this direction we plot x1, and in this direction we plot x2. This is say x1 is equal to 1. So, this is the point 1 0, and this is at x2 is equal to 1, which corresponds to 0 1. Okay. So, this is the complete space. So, whatever input vector we pick up, we have to pick up from this space, all right. And similarly we can create a weight space. Okay. Let us say that the weights are restricted, okay, that all the for all the wj vectors we choose that w1 is lying within -1 to +1, w2 is also lying within -1 to +1, let us say it is like that. Okay. So, what happens is that if we plot the weight space, okay, let us say that here we have got w1 and here we have got w2. So, maybe that for neuron 1 the w1 w2 initial vector will lie over here, w2 it is here, w3 it is here, like that different vectors will be lying in different places. Now, what we are doing initially is that we are only trying to, if you have any difficulty in understanding the concept of the spatial location of the neurons, let us forget about that. Let us say that we only do some indexing of this neuron, just some indexing, and let us say that because there is a because we want to organize ultimately that in the form of a two dimensional lattice. So, let us say that we follow a two dimensional indexing system. That means to say that the neurons will be denoted by, let us say, m comma n, where m is the index in the x1 direction and n is the index in the x2 direction, or I mean x and y direction. So, in 2 dimension their indexes are called as m and n. So, we index all these neurons. Okay. So, when we index all these neurons, that means to say that we are in a position to determine for any neuron, I mean if we happen to pick up any neuron, okay, having an index m comma n, then surrounding that neuron there will be I mean all other neurons in the neighborhood, like m minus 1 comma n, m n minus 1, m minus 1 n minus 1, all these things will be the neighbor to the m n neuron. Okay. So, okay, let us I mean forget about the connectivities for the moment. Let us say that now what we do is that we simply try to I mean indicate the positions of the initial weight vectors of the neuron. Let us say that we pick up the neuron 0 0, its initial weight vector supposing is here at this point. Supposing we pick up the next one, that is 0 1, its initial vector I mean its initial weight vector is here in the W1 W2 space. Supposing the next one's initial vector is here. Okay. Like that, the initial vectors will be organized in different places, because initially it is not according to any arrangement, we are just randomly initializing it. Okay. Now, what we can do is that, I mean just to I mean depict it properly in our diagram. Okay. See, normally what we do is that we try to connect the neighbors by lines. So, those lines are our imagination just to indicate the connectivities. So, supposing if this is the 0 0 neurons, I mean neuron having index 0 0, the vector corresponding to that. Okay. Now, this is connected to the neuron at 0 1, this is connected to the neuron at 1 0. Okay. So, 0 1 supposing is here, and supposing 1 0 is lying here. Now, 1 0 is connected to 1 1, maybe that 1 1 vector is lying here. Okay. Now, again 1 1 is connected to 2 1, and supposing 2 1 is lying here, and supposing that 2 1 is connected to 2 2, it is lying here. Okay. And supposing 2 2 is connected to 1 2, and 1 2 is lying here. So, like this we will be tracing out some zigzag, I mean some arbitrary zigzag paths, all right, if we try to connect all these neurons, okay, whose weights are very haphazardly arranged. So, these lines that we have drawn are only to show our imaginary connections, okay, between all the neighboring MNs, all right. Now, what happens is that given this type of an initial weight vector, we just place some, I mean we just happen to pick up some input vectors. Supposing the input vector that we pick up first is this one, the second input vector that we pick up is this, the third that we pick up is here, fourth that we pick up is here, fifth is here, sixth is here, seventh is here, eighth is here. Like this, the input vectors are, I mean we pick up large number of input vectors. Okay. And supposing this is a kind of an input vector arrangement that we have got, I mean that we pick up the input vectors. So, all the positions of the different input vectors are indicated over here. Now, look at this. Here I tried to make the x1, I mean the distribution of the input vectors to be uniform in this x1 x2 space, but I cannot make it exactly uniform. Like you can very clearly see that in some regions the concentration of the input vectors is more. So, the probability of picking up an input vector from this space is much more than the probability of picking up an input vector from this space. So, naturally the statistical distribution of the input vectors is not uniform actually, I mean it is varying. Now, what will happen is that, okay, after feeding these inputs, okay, we try to train this network, and here training means what? That supposing we have fed the first input vector, supposing this is the haphazard arrangement initially. So, these are all the arrangements of Wj0. So, Wj0's arrangement is shown out here. Okay. Now, what I will do is that supposing I feed the very first pattern, supposing I pick up the first input vector and I feed it. Now, all these L neurons which are there here, they will compete with each other. One of them will be the winner. Okay. Supposing some index, let us say I mean M1 comma N1, that is the winning neuron index. Okay. Now, it will be not only the winning neuron, but also its surrounding neurons which will get excited. So, M1 minus N, M1, N1 minus 1, all these neurons will get excited and all the neighbors will get excited in accordance with their neighborhood function, which I tried to describe yesterday. Okay. So, what happens that in the process, okay, all these M1 N1 neurons, okay, I mean all that one of them will be the winner and the winner will be taken closest to the x vector, correct, the x vector which I have picked up. So, even though initially it was here, okay, it will try to move towards here. Whether it will actually move or not will be dependent upon the eta, the learning rate, okay, but it will try to move closer to this, and not only that, it will try to drag along with all the other neighboring neurons. Okay. Now, you feed this vector, okay, someone else will be the winner and someone else will try to drive its neighbor out there. Okay. Pick up here, someone else will be the winner, it tries to pick up there. So, ultimately when you feed large number of patterns, okay, you will see that ultimately it will follow the topological distribution. So, the topological arrangement that we are having, mind you, is in the weight space. Okay. So, the ultimate weight space arrangement will be like this. Had it been absolutely uniform, okay, perhaps we would have expected a uniform, I mean the grid would have looked absolutely uniform, but now the grid may be looking something like this. So, the grid will look, I mean not exactly the two dimensional lattice, I mean a regular two dimensional lattice. It would look like a regular two dimensional lattice when the distribution is really speaking uniform, but it is not. I mean there is some non uniformity here. So, once this kind of a topological arrangement is there, that means to say the first phase of adaptation is over, okay, then what will happen is that we will go through the convergence phase. Now, what happens that it has picked up the rough locations, but there are some, I mean maybe that we have placed the neuron over here, okay, in the weight space, but actually the input vectors are sometimes distributed here also. Okay. It is close to this, okay, but not exactly. So, what it will try to do is that in the convergence phase, okay, there will be some internal, I mean some minor or some small movements of all these vertices will take place. So, this vertex may try to push up to this place, this vertex may try to push up to this place, like that during the convergence phase the same topological arrangement will be preserved, but the vertices of these will try to adjust to each other in order to fill up the whole space. Okay. I mean the space in which this x1 x2 vector is distributed, right. So, this is the kind of clarification that I wanted to give, and now I think that the topological ordering concept, okay, should have gone clear in your mind. In fact, I was telling in the last class that when I had first talked about the topological ordering and tried to give this initial arrangement, I was looking at the face of the students and I found that something has definitely gone above the head. And now, I mean when I see the same people's face once more, okay, I find that now they are convinced that yes, there is a definite topological ordering that is followed. All right. So, now that we have followed one of the very important properties of the I mean self organizing map, okay, we can move over to the actual topic of the day, which is about the vector quantization. Okay. Now, vector quantization is something which is followed in the data compression. Okay. In fact, I mean, just to tell you that neural networks are being increasingly used, okay, in applications which involve data compression. Okay. And we have seen, I mean, we had got a feel about it when we were talking about the principal component analysis, because there we saw that there was essentially a dimensionality reduction that we did by picking up the largest of the eigenvalues and then, I mean, projecting the input vector into those eigenvectors which are corresponding to those largest eigenvalues. So, that was very useful, and likewise even the self organizing map also can be used for the data compression. In fact, I mean, we can present the concept in this. Let us say that we have got a continuous input space. Okay. So, here what I draw is a continuous input space, H. Okay. So, this H is actually an m dimensional space, but I have to somehow draw it. So, this is I mean, some space that I have created in m dimension, and out of this I can pick up my input vector. Supposing I happen to pick up an input vector x vector from this continuous input space. Mind you, this is continuous. Okay. Now, what I have got in the self organizing map is a discrete output space, because I have got only limited number of neurons. Okay. I have got either 10 by 10 or 20 by 20 or 30 by 30, whatever be the number, but ultimately it is a limited space. I mean ultimately it is a discrete output space. So, we have got a discrete output space. Let us say that this is the discrete output space that we have. Okay. I am unable to draw it in a regular way anyway. So, supposing this is the discrete output space. Okay. So, and we call this discrete output space. So, this is the discrete output space. We call this space as the space A. Okay. So, now what we are having is that this x vector, the input vector, definitely belongs to the continuous m dimensional input space H. So, H is actually R m, I mean H is in the R m space. So, this is so x vector is belonging to H, and the discrete output space is created here. So, essentially what we are having as a feature map is a mapping. Essentially what the feature map or the self organizing map is trying to do is to map this x vector into this discrete output space, isn't it? So, essentially it is a nonlinear mapping definitely. Okay. So, we call this mapping function as the phi function. So, what phi does is to map from the input, the continuous input, that is H space, into the discrete output space, that is the A space. All right. So, now this is the way in which we can imagine, and let us say that this x vector is actually mapped into some point, let us say here. Okay. Supposing after feeding this x vector, okay, this is the winner, this neuron happens to be the winner. So, we get the I mean I of x, okay, that means to say in the competition this is supposing the I of x, okay, the winner. So, this is the winner position which will be taken very close to this x vector's position, okay, but it is, mind you, an approximation, because it is in the, this one is in the discrete space. So, that is why it is an approximation of the continuous space. So, what the discrete output space is doing is an approximation. Okay. So, now what happens is that now that Ix is the winner and Ix's position is arranged as close to possible as that of the x vector. Okay. Now, if using this Ix I try to do a reverse mapping, that means to say that from the discrete output space, if I try to map back again to the input space, okay, given this point Ix, Will I come back exactly to this x vector? No. Okay. I will be coming to some other point, okay, x prime vector, let us say. I will be coming to x prime vector, which will be different from that of the x vector. So, the distance that exists between this x vector and the x prime vector will be the error that I incorporate, and that is the error in the process of mapping it into the discrete space. So, what we are doing is effectively the continuous space where there can be a large set of values, say, okay, is being mapped into the discrete space having a limited number of neurons, okay, and my code word will be consisting of how many code words? As many neurons as I have. If I have 100 neurons 10 by 10, then I can only encode all these input vectors using one out of this 10 by 10. Okay. So, essentially here I have got a limited resource from which I try to encode a large continuous space. I may be having, let us say 25 dimensional input vector, okay, supposing m that we are choosing is of dimension 25, okay, but I may be mapping it to a 10 by 10 space, okay. So, I mean essentially what I am doing is that from a large space I am going over to a small space, okay, and I will be able to do a data reduction or data compression in this process, okay. So, let us now go more into this approximation theory, okay. In fact, this you can look at it, I mean this mapping from x vector to ix and then the inverse mapping from ix to x vector, this whole process you can think in terms of as if to say that this x to ix mapping is a process of encoding. It is being encoded into the discrete output space, and the reverse mapping from ix to x prime vector is the process of decoding, and x prime vector is the reconstructed vector for x. Okay. So, essentially what we are imagining or modeling is that we have got an input vector x here, okay, and then we are having an encoder, okay, which we are calling as the, let us say, c of x. So, c is the encoder function, okay, and we are getting a code which is c of x vector, and then this will be passed through a decoder. Okay. Now, I am not modeling the any channel noise now. I mean actually speaking, in the communication what we are having is that after the encoder, okay, it is put into the communication channel, and the communication channel can have some noise in it. Okay. So, that we are, I mean we are for the time being assuming a noise free model. Okay. Now, what we are doing here is that this code c x, okay, will be passed to the decoder, and the decoder function we are writing as x prime vector c. So, what the decoder will try to do is to get back this vector x, but it will not get x exactly, it will get x prime. Okay. So, this is the model that is followed by this type of a mapping, and supposing what we are having is that this distribution, let us now assume some distribution of this x vector in the continuous space H. So, let f x of x be the probability density function, let f x of x be the PDF of the x vector. Okay. Now, the optimum encoder decoder scheme, I mean we can call this thing as optimum such that, I mean supposing we choose a distortion measure, that the distortion measure between x and x vector, and what we want to do, we want to minimize this distortion, isn't it. So, let dx and x bar, dx comma x bar is the distortion measure, or let this be the distortion measure between x vector and x prime vector. So, we want to minimize this distortion. Of course, we do not want to minimize just the distance between these two x and x prime vector, but we want to minimize the average distortion, because actually speaking we will be having, we will be picking up a large collection of these x vectors. Okay. So, on an average we would like to see that this distortion is minimized. So, our C function and the decoder function, so the encoder and the decoder functions should be chosen in such a manner that our average distortion should be minimized. So, that is our motive. So, average distortion should be minimized. So, let us first express the average distortion in terms of what we have already defined in quantities. Okay. Now, average distortion, let us call it as D. So, we are indicating this average distortion to be equal to integral of, okay, again introducing this half. Okay. You know the reason that naturally when I talk about half, I must be doing some differentiation and there must be some squared quantity, and I just want to nullify this half with the 2 that I will get from the differential. So, always that is why we will be writing it as half. Okay. Anyway, within the integral sign, what we have to do is to take f x of x, which is the probability probability density function of x vector. This you multiply by d of x comma x prime vector, the distance between this, okay, and dx vector. Okay. Now, x vector is an m dimensional vector. So, what we have to do is to integrate in the m dimensional space. So, the integration that I am considering is over the entire space. So, if this H is the continuous space, we have to integrate it over the entire space. So, that is why in the m dimension I am showing the limits of this to be minus infinity to plus infinity, because it is a continuous input space assumed. Okay. So, this will be the expression of the average distortion, right. So, now what is the form of this d of x comma x prime? Now, the best measure that, or one of the popular measures that we take for dx comma x vector is the Euclidean distance between the two. So, d of x comma x vector, d of x comma x prime is equal to the Euclidean norm x minus x prime square. So, this is equal to, just the matrix vector form of it is to be written as x minus x prime transpose x minus x prime. So, this is this one. So, now if we put our Euclidean distance definition into the integral of equation 1, supposing we call this as equation 1. So, in light of this, the equation 1 may be rewritten as the d equal to half of integral minus infinity to plus infinity dx vector f x x. I just brought this dx earlier, that there is no problem, x minus x prime, okay, whole square. So, this is our equation number 2. All right. Now, what we have to do is that we have to fulfill, to minimize this d, we have to fulfill two conditions. The first condition is that given the input vector x vector, given the input of x vector, given x vector, choose the encoder, that is C is equal to Cx, to minimize simply the Euclidean distance between x and x prime C. Okay. So, that is the first requirement. In fact, this is called as the nearest neighbor encoding. In fact, what we are essentially doing, you can see that by mapping from the input space, continuous input space, to the discrete space, what we are doing is that we are only making the nearest neighbor as the winner. Okay. So, it is there that it is moving. So, it is a nearest neighbor encoding. Okay. So, this is the condition 1, and now the condition 2 that one has to fulfill is the decoder condition. So, which means to say that given C, okay, compute the compute x prime is equal to x prime C, okay, all in vector notations, okay, as the centroid of the input vectors that that satisfy this condition 1, as the centroid of x vector fulfilling condition 1. I will just explain what I mean by now, I mean what I mean by this line. Effectively, you see that from the x, okay, we are encoding into the discrete space, okay, the diagram that we had shown here, okay. Let us go back to this, and from here it gets mapped back to x prime. Now, what happens is that we can pick up another vector which is close to this x vector, and that may also get mapped by the same another vector very close, I mean in the very close neighborhood, this also get mapped by this, okay. So, what we are trying to say is that whatever we feed, okay, ultimately it will indicate that the, I mean this vector will be positioned, okay, this lattice position will be the centroid of all these x vectors, okay, which are causing this to be the winner. So, that is like the condition 2, okay. I mean if you try to imagine in the way of the self organizing map, okay. Now, this aspect actually is called as a vector quantization. I mean this whole thing, that is from the continuous space to the discrete space by dimensionality reduction, is the type of the concept which is followed in vector quantization, where we can have a large collection of regions, but those regions, every region will be encoded by one code given in the code book, okay. So, that is the vector quantization concept, and I mean the self organizing map is very much amenable to this. In fact, just to show the capability of the self organizing map, okay, and more so because we have introduced not only the winning neuron, but also the neurons surrounding to this for the topological ordering. So, that is why this noise free model of the encoder decoder will not be of much use to us, okay. What we have to do is to introduce the noise component also, okay, just to model the self organizing map, okay, into this vector quantization, okay. So, what we do there is that we slightly change the encoder decoder model and try to introduce the noise. So, let us say that we have the input vector x vector, okay, and then we have the encoder. So, this is the encoder C of x, and then we have the code coming out of this, and then we have got an additive noise. So, supposing this is the noise, let us say nu, okay, and then we are just this noise term added together will come to the decoder, okay. So, this is the channel effect, and then comes the decoder. I mean although this is an analogy to the communication, mind you, okay, and we will be talking specifically about the analogies little later on, the encoder decoder model analogy with the self organizing map, and here we will be having the reconstructed vector, that is x vector, okay. So, the modified form of the expected distortion. So, the expected distortion that I had already written down now gets modified, okay. So, how it gets modified? Simply that we were earlier writing it, I mean you see here we were writing it as x minus x prime, and what was x prime? X prime was nothing but c of x, okay. So, it was x minus c of x vector, okay, the coded, and here what we are going to do is that we are going to just put it as no, it was actually x prime of Cx, x prime of Cx was there. Okay. Now, instead of writing it as x prime of Cx, we are going to write it as x prime of Cx plus nu, okay, the noise term. Okay. So, the modified form of expected distortion will be d1 equal to half of integral minus infinity to plus infinity dx vector fx of x vector, okay, and then we have this term coming in, okay, you will be able to follow it soon, d nu pi of nu, I mean nu is the noise and pi of nu is the probability density function of the noise. So, what we are doing is that we are first integrating this into this space. Okay. So, this whole thing will be the the distortion measure. Okay. The distortion measure for x vector will be what? This entire integral expression. And what is that integral expression? Okay, this term we have written, and then it is x minus x prime of, the argument of x prime is not just Cx now, the argument of x prime is Cx plus nu. So, this is Cx plus nu, okay, and we have to take the Euclidean norm of this. So, this is square of this and pi of nu, okay, this is the PDF of the noise. So, this integral expression is now the error that we are, is the distortion that we are having for the mapping of x vector into x prime, okay, and we have to just multiply it with fx of x, that is the PDF of x with dx vector, and integrate it over the entire input space. Okay. So, this is the modified form of the PDF, and then what we have to do is that in order to that, given this model, we have to find out the optimum encoder and the optimum decoder. Okay. Now, to find out the optimum encoder, what we have to do is to differentiate this d1 expression with respect to C. Okay. Now, that we have got a term involving C, okay, we can find the optimum decoder by finding, optimum encoder by computing dou d1 dou C vector, and this, if you evaluate this, it works out as this is equal to half of fx of x vector integral minus infinity to plus infinity d nu pi of nu, okay, dou C vector norm of x vector minus x prime of C whole square. Okay. This is at the point C is equal to Cx plus nu. Okay. So, this is for the optimum encoder. We have to equate this thing to 0 and solve. Okay. And for the optimum decoder, what we have to solve is optimum decoder, what we have to solve is by equating dou d1 dou x prime C to 0. So, dou d1 dou x prime C's expression is again evaluated from this integral expression itself is equal to minus of integral minus infinity to plus infinity dx if x of x pi of C minus Cx vector, okay, this multiplied by x minus x prime C. All right. So, what we have to do is to set this thing to 0 and then solve for x c. So, we have to first solve for the encoder and then we have to solve for the decoder. Okay. Now, the condition that we had put forward earlier, that is to say in the noise free encoder decoder model, we had given the condition 1 and condition 2. Condition 1 was the nearest neighbor condition and condition 2 was the reconstruction vector condition, where we had said that it will be mapped to the centroid. Now, in this case with the noise model, the condition 1 and condition 2 slightly gets modified, and what are they? The modified condition 1 that works out as is to minimize, again we define some distortion measure D2, and what is that distortion measure D2? That is nothing but, you can see it is this. Okay. This we have to modify. So, this minimization of D2 is given by that D2 is defined as minus infinity to plus infinity d nu pi of nu, okay, and the Euclidean distance x minus x prime, whose argument will be c x plus nu. Okay. So, x minus x prime with this argument, squared norm of this. Okay. So, that becomes our D2. Okay. And the modified condition 2 will be obtained by solving this term, that is to say the optimum decoder term, that is setting this dou d1 dou x prime c to 0 and then solving for x prime c, and there the solution of this x prime c is given by integral minus infinity to plus infinity dx f x of x, okay, pi of c minus c of x, okay, x, and in the denominator it will be minus infinity to plus infinity dx f x of x, okay, pi c minus c x, okay, not this x term. Okay. So, this is the x prime of c, okay, which is essentially the equivalent form of the centroid. Okay. This is basically the centroid that you will be getting, only thing is that this is under the noise term. Okay. So, this model actually is very much analogical to what we have defined as the self-organizing map algorithm. Okay. Let us see that, I mean, let us try to present this analogy. So, we have the encoding decoding model listed on this side and the SOM algorithm listed on this side. Okay. Now, if we talk about the encoder part, that is C of x in the encoding decoding model, what will be its equivalent analogy in the self organizing map? What will be the analogy of the encoder? You do not have to look at the equations, just again go back to our concept of discrete space approximation. Yes, that is I of x. I of x is the equivalent of the encoding process. So, what is encoder C of x for the encoding decoding model? It is weaning neuron I of x for the self organizing map. Okay. Now, what is known as the reconstruction vector, I mean in the encoding decoding model we have shown the reconstruction vector x prime of c, and what is its equivalent analogy in self organizing map? The answer should come from you. Yes? Weight vector, that is correct, the synaptic weight vector, because the synaptic weight vector is ultimately approximating the input vector. Very correct, thank you. So, this is the synaptic weight vector. Wj, and you see that I have also got, I mean in the encoding decoding model where I had shown the noise term also, I have got the probability density function pi of c minus c x vector. Okay. I had shown that. Okay. And what is its equivalent in the SOM algorithm? Neighborhood function, that is correct, because you see this c minus c x is something where we have got the noise built in. Okay. Noise means, equivalent to that, there is a neighborhood function that not only the winning neuron, but we are also exciting the neighborhood of this. So, the equivalent in self organizing map is the neighborhood function h of j I x vector, right. Now, actually this self organizing map, so these three analogies are highly interesting. In fact, that is what makes the self organizing map as a very good candidate for vector quantization, which one can use in the data compression applications. Okay. In fact, we could talk about some of the practical applications of SOM in details, okay, but because of the time constraint, okay, such discussions we could not have. Now, we are going to also okay, now I'm also going to tell you about a few important properties of the self organizing map. Now, two important properties which we have already seen is, number one is topological ordering, which we have already seen, okay, and understood also, and the second property is the approximation property. Okay. So, these two properties we have accepted. In fact, the approximation property itself leads to the vector quantization concept, okay, and there are two more properties for the self organizing map. So, if we call the, let us list out the four properties. If we call the property 1 as the approximation, okay, which we have just now described, okay, and if we call as property 2 the topological ordering, which also we discussed, and if as property 3, and then as property 3 we can mention about the density matching. Okay. Now, just to explain what density matching really means, let us go back again to this diagram. You see, here what I intended to do initially was to make this x1 x2 vector, okay, distributed in a uniform way. We wanted to have a uniform distribution of x1 x2 vector, okay, in this x1 x2 space, but we could not make it uniform. Okay. Perhaps what might happen is that supposing I get more concentration of vectors over here, and I get less concentration of vectors over here. Okay. So, what can you expect out of the topological mapping? It will shift towards that, and not only that, because there are large number of inputs over here, okay, it will try to pull in more number of neurons. So, there will be more number of winning neurons there. So, more of the neurons will try to accumulate there. That means to say that even for the neurons also, when we find out the topological arrangement, we will be finding that the ultimate neuron positions will be more, with more resolution in this area as compared to the neurons which are located in the sparse region. Perhaps in this region only one neuron will be sufficient to resolve, but whereas here maybe 4 neurons will be required to do it. So, essentially again the topological arrangement that we are having, there is not much of a qualitative difference between the property 1 and property 3, but the property 3 tells that the arrangement of neurons that we will be having at the end of the convergence phase, okay, will be such that the density of the neurons, okay, in this space ultimately, in the weight space ultimately, we will be having the density of that matched to the density of the input vector itself. Whatever characteristics the input vector space is showing, okay, will be ultimately shown by the weight vector. That is the concept. Okay. If you have understood that, you have understood the self organizing map properly. So, that is the density matching part of it, and then the last property of it is the feature selection. Okay. That basically is also something not very new. Okay. Now, we have got an input space, okay, with nonlinear distribution, is not it? Essentially, it is a nonlinear distribution, and using the, and even from that we are able to pick up the best feature out of a nonlinear distribution of input space. So, this is also a very important property. In fact, it logically follows from the other properties itself. Okay. So, this is what we have for the self organizing map, a very useful thing, okay. And we have studied actually in the light of Kohonen self organizing model, okay, where we have presented it in a more general way. So, that is all for this class. Thank you very much.